Good evening, everyone. Am I audible and are my slides visible? Okay, so let's get started with today's live session. Today we will be discussing week 5 content. Um, Let me go to the window. Yeah. So in week five's lectures, the main topics that were covered were correlation, covariance, linear regression, multiple regression. So these concepts were covered and how to perform these operations using R was also covered. So first, let's discuss and revise what was in the lectures, and then we can discuss the codes that were used in the lectures. So in the first lecture of the fifth week, the first thing that was discussed was covariance. So covariance is a metric that will tell you whether uh, if a variable x is increasing, then the corresponding variable y will it also be increasing or decreasing. So that is what the covariance will tell you. And the formula for covariance is basically, so to find the covariance, first you have to find the mean of both the variables, and then you have to subtract each value from the means and multiply the two together and find the mean of the multiplication. So that is what the covariance formula is. So I can just simplify it. So first find the mean of each variable, in this case x and y, and then subtract each value from the mean, and then you have to multiply the subtracted values, and then you have to find the mean. So because there will be, if there are 10 values of x and y, so there will be 10 numbers here. You have to find the mean of the above, the this multiplication basically. So that will give you the covariance. And if you simplify this formula, you will get a simpler formula where you just have to multiply xy and find its mean, and then subtract it from the multiplication of mean of x and mean of y. So if you uh, expand this, this will be the formula. And finally, this covariance, it will just tell you whether the variables are increasing together or decreasing together, but it won't tell you how much, what is the strength of the relationship. So to get the strength of the relationship, we have to look at the correlation function. So there are two types of correlation coefficients. One is the Pearson correlation coefficient, and the second is the Spearman correlation coefficient. So this Pearson's correlation coefficient will tell you how much linear the data x and y are. How much is the linearity in the relationship. So and then it varies from -1 to 1. So -1 means it is negatively correlated, meaning that if x is increasing, y will be decreasing. And 1 means they are positively correlated and the correlation is perfect. And 0 means the two variables are independent. So if this is x and this is y, I hope you can see what I'm drawing. So this, if it is a straight line, it will be a correlation of positive correlation between x and y. And if they are not, and if it is when, so in the second case, when x is increasing, y is decreasing. So in this case, the correlation will be, or the Pearson's correlation coefficient will be negative. So this Pearson's correlation coefficient, it will only work for um, linear relationships between X and Y. But sometimes the X and Y may be correlated, but maybe they are not linear. So like in this case, so in this graph, if you see, X and Y are not correlated, but still they are increasing linearly. Like I've drawn some examples. So in this case, if you see, the straight line fit will be like it will be slightly away from the actual curve. So the correlation coefficient will be less, even though they are positively correlated. So to avoid this issue, uh, because in this case it is a monotonically increasing function, but it is not linear. So to avoid this issue in the case of monotonic functions which are not linear, we use the Spearman's rank correlation coefficient. So here, instead of considering the correlation between the values, the correlation is for the rank data. So rank data means, for example, if X is uh, 4, 3, 5, and 8, the lowest one, this will be rank 1. So the rank will be given based on their um, value. So this is what is called as rank data. And similarly, this is also ranging from -1 to 1. So and 0 means they are independent. So this is about the correlation coefficients. And one more correlation coefficient is the Kendall rank correlation coefficient. So in this case also, it is based on the rank of the coefficients. Uh, and so for every pair of X and Y. So suppose I'll give a simple example of just three values of X and Y. Maybe X is 1, 2, 3, and Y is 3, 2, 7. So you have to find for each pair whether it is concordant or discordant, like these two, these two, these two, and then the other pairs as well. So if they are concordant, it means that both of the rank, so the sort order is nothing but the rank. So they are the same thing. So if the rank of both are the same, um, then they are concordant. Otherwise, they are discordant. And finally, we have to use this formula: number of concordant pairs minus number of discordant pairs divided by this is the total number of possible pairs. And one more important thing to keep in mind when you're calculating correlation is that correlation does not imply causation. So even though two variables are correlated, so for example, if X and Y are correlated, we cannot say that the increase in Y is because of X or the increase in X is because of Y. So that we cannot say. So now let's discuss the problem from the first lecture. So you can open R and use R to get the value. So you can take 2 to 3 minutes for this, and then we will discuss the code to do this. So once you have the answer, you can type it in the chat box, and then we will discuss it. Has anybody got the answer to this? Okay, so I already gave you a hint that you can do it with R. So the first step will be you have to write the data in R. So first you can declare two variables X and Y and assign them the values that are given in the question. So you can use that using the C function to create two vectors called X and Y. Okay, let me share my R screen and show you how to do it. Meanwhile, you can also try to do it on your own. Mm. Okay, so now I'm first putting the values of X into this vector using the C. So the values are 0.9126. So here I'm just typing it manually because the question is in the slide. 126, 2.45, 2.3, and 1.1. So now we have defined X. Now similarly, we can also define Y by just typing the values that are in the question: 0.2, 0.23, 0.5, 0.8, 0.61, 0.52, and 0.23. Now we have to, now in the question, they are asking to find the correlation between X and Y. So to find the correlation between X and Y, in R, there is a function called COR. So that would give you the correlation. So you just have to type. So this is the variable I will be storing the answer, and then write the correlation function. And the input to the correlation function would be X and Y. And then I can print it. So let me run this. This is done. When I write print correlation, it has so the final answer is about 0.903. So now I hope it's clear to all. Let me go back to the presentation. So these are the steps that we did. So first we assigned X the values that are given in the question. And then similarly, we declared a vector called Y and assigned the values given in the question. And finally, using the COR function, we got the correlation. And the final answer that we got was about 0.903. 903. Yeah. Any questions? Okay, I hope it's clear to all. So let's go to the other topics. So from the second to the fourth lectures, we covered linear regression in the lectures. So linear regression is basically like fitting data. So for example, have some, if you want to find out how X and Y are related, and you have some, maybe you have done some experiment and you have some experimental data, then you can fit it to the form, to the linear form. So we are fitting it to a linear equation. That's why it is called as linear regression. So you can fit it into the y is equal to mx plus c form based on the data that you have. So it is an example of data-based modeling. So I can maybe show you graphically. So maybe your experimental data looks something like this. So you have the X and Y axis, and you have data points like this. And now you want to fit a straight line to your data points. So many kind of lines are possible. Maybe one line is like this, this is the first line, second line, and maybe the third line is like this. So there are different kinds of lines that can be fit, but how do we find the best fit line? So here, just by looking at it visually, we can say that maybe line 3 looks like the best fit line because it is going through most of the data points. But mathematically, how do we get that? So to get that, we use a method called sum of minimizing the SSR or sum of squared residuals. So the idea is that if you have a line, so this is the fitted line, and you have maybe some data points are on the line and some data points are above the line and below the line. If it is a best fit line, then the distance of this line from the points will be minimal. So according to the model, this sorry. Mm. So according to the model, this should be the value of y at maybe this particular x1. But our model is wrong because the actual value of y is over here on the top. So this is a residual or the difference between the actual value minus the predicted value. So if the model is good, then this residual has to be minimal. So because the better the model, the closer the actual values will be to the predicted values. So that is the idea here. We have to minimize the sum of the squared residual. So in this case, there is maybe this is the first residual, let's say R1, and this is the second residual, and this is the third residual. So the residual can be, in this case, it is positive, and in this case, it is negative. But we are only interested in the value of the residual and not in the uh, whether it is positive or negative. So that's why we take a square. So in this case, this R1 square plus R2 square plus R3 square, this is the value that we are trying to minimize to get the best fit line. So this is the idea behind the least squares method of doing a linear regression. So based on this concept, you will get a formula that for y is equal to mx plus c. To find the slope, you can use this formula, covariance of xy by variance of x. And similarly, for then once you get the value of m, then you can get the value of the constant. So now let's discuss this problem that was given to you in the lectures. So here they have given, uh, you have some data, and using this data, you have to find the best fit values of A and B. So they are asking to perform linear regression using means, variance, and covariance. So I can give you a hint that you have to use this formula for M here. And you can use R to do it, so it will be quicker. So this slope formula, M is equal to covariance of x comma y divided by variance of x. You have to use this formula here. So here also the first two steps will be same as what we did last time. You have to input these two values into a vector, and then you have to find their mean, variance, and covariance. So if anybody gets the answer, you can put it in the chat box. I'll give you a couple of minutes to try it by yourself. So if anybody has found the mean, what is the mean of G1 and what is the mean of G2? So for the mean, the function that you have to use is just mean. So for G1, you just have to write mean and within the brackets G1. So first input the values of G1. So make it declare it as a vector and then write mean of G1, you will get the mean. So if you have got it, you can type the mean of G1 in the chat box. Has anybody got it? Okay, I think some of you have got it. So I will share my R window and we can check if it is correct or not. So if you have got the means, then you can then find the variance of G1 because that will be in the formula for the slope, right? So after finding the mean, you can find the variance of G1. Okay, so here I have already typed the values of G1 and G2. And now let's find the mean of G1. Sorry, I did not run this line. So G1 has been defined now and G2 as well. So the mean of G1 is 1.9711. Now let's find the mean of G2. Mean of G2 is 3.325. So now we have the means. And now if you look at the formula to get the slope is covariance divided by variance. So the next step would be to find the covariance and the variance. And if you look at it, the variance is for x. Here in our example, y is G2, x is G1, and in like if you compare it to y is equal to mx plus c, y is G2, x is G1, and the slope a or m is a, and b is the constant term. So let's first find the slope. So for that we need the variance of G1. Has anybody got it? Let me check the chat box. Okay, anyways, I think you're still working on it. So for the getting the variance function, you just can write this VAR, and we need the variance of, sorry. Actually, let's also assign these values. Mean G1 to variables. So then it will be easier to put it in the formula. So now we have mean G1 and similarly, let's also get mean G2. Sorry. And similarly, variance also, let's assign variance G1 is equal to VAR of G1. So now we have got the variance. So this will be the denominator and the numerator is the covariance. So covariance of G1 and G2 is equal to, so for variance, the function is COV, VAR, and for covariance, it is COV. And you have to write which two variables you want the covariance for. Okay, I think I have made a mistake in these values. Maybe I missed something. So let me check. 25, 1.32, 62, 97, 2, 2.2, 2.3, 2.8, 2.6. So here it is giving incompatible dimension error. So maybe I have missed a number, or maybe I have added a number extra. So I'm just checking. 2.25, 3.5. Okay, so instead of 3.4, I have written 3 comma 4. So that is why its error is coming. So I will just redefine. I'm running this line again so that this mistake that I corrected is being taken by the code. So now let's try and see. Yeah, so now there is no error. Now we can use the formula. So the formula for the slope, or in this case, A, is covariance of x comma y divided by the variance of x. Variance of x. And here x is g1, y is g2, and x comma y, yeah, that's all we need. And the slope m is a. M is equal to a. So to a, let's assign, sorry, I'm used to coding in Python. So in Python, you have to use the equal to for assignment. But in R, this symbol is the assignment symbol. So A will be covariance of x comma y is nothing but covariance of g1 comma g2 that we calculated, divided by variance of x is nothing but this variance of g1 that we calculated. Variance of g1. So let's run it. And now if you say print A, we will get the answer. 1.446589. So we have got the slope now. So the slope is done. Next thing is we have to get the value of the b as well. So if you look at the formula in the 7th slide, you can find the slope once you have the um you can find the constant term once you have the slope. So the formula is c is equal to y bar, or so instead of mean, I'm putting this y bar minus m into x bar. Or let me write it with these square brackets to indicate the mean. So here c is nothing but b. So b is equal to y bar is mean of y. Here y is g2, right? So it would be mean of g2, mean underscore g2, this variable that we defined, minus slope is a, multiplied with, if you're confused, you can also use this bracket, mean of g2. Slope multiplied by mean of the x, and x is g1 here. So now let's print the value of b. Okay. So the value of the constant term that we are getting is 0.47. So I hope this is clear to all. So this is very important. So if you have any doubts, please ask me, because this linear regression, in the upcoming lectures, we will be doing it often in the upcoming machine learning lecture. So better to get your concepts cleared. And so not just about how to calculate it, but you should also be knowing how to calculate it using R. So let me go back to my presentation. Meanwhile, if anybody has any doubts, please raise your hand. So this was the problem. We solved it with this formula, covariance of x comma y by variance of x. And we used this code to do it. I'll put that as well in the slides for your reference. And finally, when we got these, I'm also putting the outputs so that, so please, you have to try to run these codes by yourself and get the answers. If you just listen to me, then that is good. But the best thing would be to write it by yourself, write the codes and try it out by yourself. So, and the B output also I'm putting here. So when you try to do it on your own, you can cross-check the outputs with what I have put on the slide. Okay. So we have covered the second to the fourth lectures on linear regression. And then the next lecture was about multiple linear regression. So in the previous slide, we had just one variable x1 in linear regression, but in multiple linear regression, we have many variables x1, x2, xk, etc. And here also the concept is similar, that we have to minimize the SSR, or sum of squared residuals. So that is nothing but yi minus yi bar. So one is the uh, model predicted by the model subtracted by model actual value in the data. So when it comes to multiple linear regression, there is an important uh, issue that you have to keep in mind when you are trying to study multiple variables. So here, if you remember, let me write it down. So m1 x1 plus m2 x2 plus m3 x3 plus some constant term. So here the variable y is dependent on many variables x1, x2, x3 and so on. But sometimes it can happen that these variables they themselves are correlated. There is they are not independent, but maybe x2 and x3 are correlated. So if this is the case, then we will run into this problem of multicollinearity, because this is when we use linear algebra to get the values of m1, m2 and m3, we will be using matrices. And in matrices, if we have linearly dependent rows or columns, then it will be difficult to solve the equation. So that's why this multicollinearity is a big problem. So to check the multicollinearity, first you have to check whether any of these variables are correlated. So you can check it using the Pearson's correlation, and you have to do it for each pair. So you have to check if x1 and x2 are correlated, x2 and x3 are correlated, x3 and x1 are correlated. So even if any one pair is correlated, that will be a big problem. And there is one more concept as well, VIF. So this we will be solving a question based on this. So at that time, I can explain it better. So we have covered the concepts that were covered in the lectures. So after this, now let us solve some additional MCQ problems, and then we will be discussing the codes. So this is the first question. You can take a couple of minutes to read and understand the question and try to answer it, and you can put the answer in the chat box. Then we will discuss the solution. So anyone has got the answer yet? It's a fairly simple question. So you can try to write it in the form of y is equal to m1 x1 plus m2 x2 and so on. So this is the idea that you have to write it in the form of a linear regression. So here there are two variables, right? X1 and X2. So one is the soil salinity, one is the soil moisture content. And apart from that, we also have the beta naught term. So we have to find these three values and these will be in the coefficient vector. So there are beta naught, beta 1, beta 2. There are three values. So the answer is 3. Let's go to the next question. So they are asking which of the following is used to measure goodness of fit in multiple linear regression. So this multiple is important here because here in multiple linear regression, you can have as many multiple independent variables and not just one. So the option A is Pearson's correlation coefficient. So the Pearson's, sorry. So this Pearson's correlation coefficient will just give you the correlation, but it will not, it cannot be used to say how much it is, the fit is. And option B is coefficient of determination. So let me check the chat box if any of you have got the correct answer. Okay, so some of you have got the correct answer. So this coefficient, option B is coefficient of determination. So that is nothing but R square. So R square, again, it will tell you how well a statistical model predicts an outcome. But the problem with this R square is that it does not take into the consideration how many variables are used. So The problem is that sometimes people use many variables to improve the R square value, but it is not a good practice. It is better to keep your model simple with the minimal number of variables. So to penalize this increasing number of variables, there is another measure called the adjusted R square. So in adjusted R square, the denominator will be having the n term or the number of variables term. So it will penalize having more and more variables, because as n decreases, the adjusted R square value will decrease. So for multiple linear regressions, it is better to have this adjusted R square rather than just R square. And finally, ANOVA, it is to find whether different groups are different or not. So it is not it cannot be used for this purpose of goodness of fit. So any doubts? Okay, if not, let's go to the next question. So here we have a multiple linear regression model. Y is equal to beta x plus delta z plus kappa w plus alpha. So here beta, delta, kappa, sorry, and alpha are the model coefficients. So here what will be the null hypothesis they are asking? So it's already going to be 8 o'clock and we have to discuss the code as well. So I'll be going a bit fast. If any of you have any doubts, you can raise your hand. Okay. So here these are the model coefficients beta, delta, kappa, and alpha. So usually I hope all of you know what is a null hypothesis. So null hypothesis means it is the opposite of what we want to test for. So suppose if we want to test whether two groups are different, then our null hypothesis will be that there is no difference between the two groups. So in this case, the null hypothesis will be that there is no dependence of y on these x, z, and w variables. So if there is no dependence, then all the terms will be zero. So the null hypothesis will be that all of these correlation terms, beta, delta, kappa, that are associated with the variables are zero. And this question is about how to perform a multiple linear regression using R. So these are the type of questions that you can expect in your exam. You will not be asked to code directly with R, but you will get these questions like how will you write the code for doing something, and you will get four options. So you have to know which is the function that you have to use, and which is the inputs that you have to give, etc. So this is also a straightforward problem. So here the inputs that you give will be, the function is lm. As you can see in all the options, it is lm. And the syntax also you have to know for the function. So the first input to the function will be which are the independent variables and the dependent variables. So here they are separated by a tilde. So z is the dependent variable here that will come first, and the other variables x and y will come here. And you also have to include the constant variable. So here we are not having any constant, so we have just put it as 0. And these z, x, and y have to be stored in some data set so that the code can access these values, this data. So that will be given as, that will be the next variable, next input, data equal to d. So the correct answer to the fourth question is option A. So you have to remember this syntax. And you don't forget to add the constant term as well. because option C is basically that, but the correct answer is option A. So this is the variance inflation factor, VIF, that we discussed. So this you can get the answer if you know the formula for VIF. So just based on the formula, you can get the answer. So the VIF, the formula is 1 by 1 minus R square. So here this R square is the coefficient of determination, or the just the normal R square that we get to get the model fit, right? So the formula is 1 by 1 minus R square. So this they are asking what is the minimum value. So when this value for this to be minimum, this 1 minus R square should be maximum. So this will be maximum when R square is 0. So then in that case, it would be 1 by 1, which will be 1. So a VIF of 1 is a good sign that it is not correlated with other predictors in the model. But if it is more than 5 or 10, then it is we might have a problem of multicollinearity. So this question is a straightforward question, but I'll just give you a few minutes to read and attempt it yourself. This is just the name of the function, right? So there are different, like some confusing options are given, but it is important to know the exact function as well. So which is CONFINT or confint. So this sixth question is straightforward. You have to know the important functions of R. So this is based on the Kendall rank correlation. So for this, I can give you some time, maybe 3-4 minutes, because some calculation is involved. And we just discussed the formula during our revision session. So you just have to apply it. Okay, so I think some of you have got the correct answer. So the correct answer is 0.25. So you just have to substitute the values. So the formula is number of concordant pairs minus number of concordant pairs divided by the total number of pairs. So we just have to substitute the values. Number of concordant pairs, it is given in the question directly, it is 10. 10 minus, and this concordant pairs is 6. And total number of pairs, they have given us 16, but even if they have not given, you can just add 10 plus 6. So that would be 16. So this will be 4 by 16 or 1 by 4. So this value is 0.25. Okay. So this is the last question. After this, we can discuss the coding part. So anybody knows the answer to this? Okay, so I'll explain what is a correlation matrix. So suppose you have many variables. Maybe you're collecting uh, data about plants or maybe some trees in a forest. And you're interested in the three different properties, maybe the height of the tree. So this will be the first variable, x1. And you're measuring the bark diameter. So that would be the second variable, x2. And maybe you're also measuring the number of branches. That will be your x3, and you have maybe some values like in meters, 10, 8, 7. Maybe this is 5, 4, 6. Maybe here you have 50. I'm just writing some random values. Okay. And you want to know whether if there is any correlation among any of these three. So I'm giving an example of three variables, but there can be multiple variables. So you will find the correlation pairwise, right? Correlation of x1, x2, and then for x2, x3, and then for x3, x1. So one of the ways to represent this is using a correlation matrix, this kind of pairwise correlation. So you will write a table. Both sides you will have x1, x2, x3, x1, x2, x3. So this number here will be for x1 and x1. What is the correlation? Obviously, they are the same variable, so it will be 1. And this middle will be x2 and x2. So this will be 1, and x3 and x3 will also be 1. So in a correlation matrix, all the diagonal elements are 1. But option A is saying diagonal elements are 0. So option A is false. And the remaining x1 and x2, maybe it is 0.2, x1 and x3, it is maybe 0.3. And one more thing you have to notice is, so here it is correlation of x1 and x2 over here. And here also it will be correlation of x1 and x2, 0.2. Sorry, not here, here. So these two values are the same. Similarly, x1 and x3, these two values, because both are for x1 and x3, these two values are also the same. So that's why it is a symmetric matrix. So it is a square matrix, it is true, because same number of variables we have to write here and here. So this is true. Number of columns is equal to number of variables. So this is also true. And it is a symmetric matrix. This we just saw. So this is also true. And in the question they are asking which of the following statements is false. So option A is the correct answer. I hope it's clear to all. So if it's clear, we can move on to discussing the codes. Let me just share my R window. Mm, Stop sharing and I'll share the R studio. Okay. So it is still in the old code. So I have taken these codes from the NPTEL website itself. So along with the lecture slides, the R codes and the data that is used in the R codes are also given. So that is the code that I'll be using. So if anybody does not have these, then you can let me know. I can type the code in the chat box. So you can run the code from there. So I request all of you also to open our studio. So I'm opening this one, lecture 4, week 5A. So I request all of you also to open it and run it along side by side. So maybe I can wait for 1 or 2 minutes for everyone to open their R studio and get this file. This is lecture 4, week 5A. Okay. Okay, so I'll get started now. If anybody has not yet opened it, you can raise your hand. I will wait for another minute and then we can start with the codes. Okay, so I hope everybody has it open. So in this, we will learn how to do linear regression with an example using R. So we are going to do this A plus BX or MX plus C that we did. So the first step will be to read the data. So this data is not reading properly. So let me copy paste the path, entire path name. So usually if it is in the same folder, the data will be read. But I have to check whether I have to update my RStudio. So that's the problem, I think. So I have pasted it as a path name. So now the data has been read. So now let's first plot the data or we can also first see what is in the data here. So just do a print statement. Yeah. So it is having data about age and the systolic blood pressure. So it is just two columns. So we can plot these two. So here, maybe we can try to plot with the age. How will the blood pressure look like? So this we discussed in the previous lecture, how to plot. So this you have to write the data frame, dollar, which column you want to plot for X and dollar, which column you want to plot for Y. And you can also give other input such as the which label you want, what is the point color you want, size, etc. So this is the value we are getting. So it seems that more or less as the age is increasing, what's happening? The systolic blood pressure is also increasing. So now to check how much is the strength of the correlation that we find, we can find the Pearson correlation using the COR function. So I hope you remember COR, the format is X, comma, Y, and you can specify the method. So X here is the age column, so D dollar age, and Y here is the blood pressure column. So that's what we have given here. And you have got the answer as 0.657. So we see that they are positively correlated with a Pearson correlation coefficient of 0.657. Next, we want to fit a model that can predict So if you are at a certain age, we want to make a model that will predict what will be your systolic blood pressure. So for that, we can use the LM function for linear regression. And let's see what is the result. So not only we have got the coefficients, we have got the intercept and the age. So the intercept is 98.7 and the coefficient for the age is or the m value, the slope value as well. And we have also got how good is the model fit. So we get the residual standard error, which is the subtraction of the actual value from the model value and the square of it. And the p-value is the p-value is quite low. And we can also find the confidence interval. So confidence interval, this you have to use this function CONFINT, which we saw in the problem solving session as well. And so once you have done the regression, you can also draw the regression line using this AB line function, which will draw a constant one. So the input will be this REG, which will have information about the slope of the function, slope and the intercept. And you can also specify others like what color you want and what will be the width. So let's try to change this and see what is happening. So now we have done the linear regression, found the confidence interval, and we have also plotted the line that we have got from the linear regression. So now let's go to the next code, which is lecture 4, week 5B. So here also we have to read some data. So I'll put the file path. So the data has been read. So it is, I think, having two columns, concentration and absorbance. Sorry, the data file's name is DNA. Yeah, so it's having one column concentration and second column is absorbance. So first, let us plot it using the plot function. Same thing that we did before. And here also you can see it seems that as the concentration is increasing, the absorbance is also increasing. And next we have to do a linear regression for this data. So linear regression, by now I hope all of you know which is the function we have to use for linear regression. We have to use LM. So then we have assigned it to the variable R1. So it has predicted the values and you can see the adjusted R square and the multiple R square or the coefficient of determination are pretty good. They are almost 0.986. And if you want a linear regression without intercept, then this plus 0 you have to mention. So that is what we discussed in the problem solving session as well. So this will be in accordance with the Beer-Lambert law. So now let's see which of the following is whether the old model or the new model without the intercept, which is doing better. So if you see this R squared, this is 0.9859, but in the previous model, the R squared was 0.9806. So it means that the second model without the intercept is the better model because obviously it is mechanistically it is based on the Beer-Lambert law. So out of the two, we have seen that this R2 is the better model. So we will be plotting this R2. So sorry. Now let's go to the lecture 6 codes. Right. So now I'm at lecture 5, yeah, lecture 6 of week 5 code. So please open this document. So this is based on multiple linear regression. So previously we just had one independent variable, one dependent variable. Now we will be having multiple independent variables. So fish.csv. So let me first read this file by putting the path name. So the file has been read. Let us first check what is in the file by using a print statement. So it's having these three columns: age, temperature, and length. So here the idea is that you have to find a model that can predict the length based on its age and the temperature. So here also the um, function is the same, lm, but here you're having many variables. So they are like last time we just had one number here. We go back here. So here you just had one variable, but since we are doing a multiple linear regression now, you have age plus temp, more than one or two variables in this case, and the data is stored within this fish file. So that's why data equal to fish. So it has done the regression now, and let's check the regression. So it is giving what is the um, coefficient for age. So it is about 27.280, and coefficient for temperature is 29.074. And it's also giving the significance value. So these both are about 3 stars of significance. So you can also find the confidence intervals to further validate the regression model. So this is the main thing you have to know here is this LM function and the format to enter the data. So here you will give the dependent variable and followed by tilde sign and followed by all the other variables you have, and they should be separated by the plus symbol. So this is the first input, all the variables, and the second input would be the data frame, which is having the variables. And the data frame columns should be matching here. So for example, if I do a mistake, instead of age, so if you see here, the name of the column is age, but I am giving ages. Now it will throw an error. Object age is not found. So not just the variable name, but even the uh, capitalization of letters has to be, you have to be careful. So here instead of small t, I'm giving capital T, then it is saying temp not found. So you have to give the exact column of the name. Then only it will work. So this is lecture 6 A code. Now let us open the B code. Copy as path name. So I'm just installing a package. Once it is done, we can run the code. Okay. Why is needed summary car package? So maybe you all can also install this car package. So I'll just type in the chat box or so I just installed it directly because it showed me a message. Otherwise, you can use this function. Install.packages CAR. So this one I didn't have to use, but yeah, if you didn't get the message, I'll put it in the chat box. You can also install this package. Okay, so now let's run the code. So first we have to read the data. So we have read it. Let's see what is in the data first. Print multi. So here it is having three columns. So we have one of it will be the dependent variable and the other three will be the independent variable. So usually this S will be the dependent variable. The last column, that is the dependent variable S, and the other columns are the independent variable. So again, we are using a LM function to do the regression. So here you can see the input syntax is slightly different because we are, so sometimes maybe in this case there are four columns, but maybe some of the real life data can have like even hundreds of columns. So it will be difficult to write all of the columns here. So in that case, if you want to perform linear regression with all the columns except this dependent variable column, then you can just put a dot. So it will consider all the columns. So you can also enter it manually. So let's check whether we are getting the same result when we enter manually versus when we use this dot method. So here we are getting these values for the coefficient of M, coefficient of P, and coefficient of R. Now let's try to do it with the other method where we manually enter the values. So instead of dot, I'm going to write P plus. So I hope you remember the syntax. P, R, what else was there? M, P, and R. Okay. M plus P plus R. And we are not considering zero intercept. So this won't be needed. Data equal to multi. So now let's also, sorry, print this value and check whether they are same or not. Minus 1.3428. So you can see that they have given the same result. Suppose you want to exclude one of the columns. Maybe we know that M is not associated with R. So then you can just remove it. So then in this case, if you put a dot, it won't work because we are removing one of the columns. So if you want to remove the column, it's better to put it manually. Now if I print it, now it will be different. Yeah. So now the values are different, obviously, because we have removed one variable from the calculation. So now, okay, fine, we have done this multiple linear regression, good, but is it valid? Because in multiple linear regression, we know that collinearity is a big problem. So to do that, we have to find the variance inflation factor. So to find the variance inflation factor directly, you can use this VIF function. But this VIF function, it is not in R directly. You can get it from the car package. So you have to first load the package. So this is similar to in Python also you have different libraries like pandas and numpy. So similarly, R also has it. So I have already installed the package. So first you have to call the package library car. Loading, so it is loading it. Now we can find the VIF. So the VIF values are all about 1 point something. So it's not bad. So it's fine. So 1 point something is quite low value of VIF. So we are not having any problem of multicollinearity. So we can trust the um, correlations that we have, the coefficients that we have got from this method. So I hope it's clear to all. So now if you want to do, you can do other things as well. So you have this multi-data frame. If you want to find the mean of the first column, you will get it. And you can also find the variance. So this is just some of the other things that we discussed in the previous lectures. So we have covered everything today so we started with the revision of the session, sorry, and then we discussed some problems, and finally we also discussed the codes that were on the NPTEL website. So that's it for today. If you have any doubts, you can ask. Otherwise, we can end the session for today. If you don't have doubts, you can leave the meeting. We can meet in the next class.